Hello, everyone, and welcome to today's graph reading group.
Where we have a very cool and I think technically a very interesting method for sampling transition paths, like sampling how along which configurations a molecule moves from one state to the other state. So let's go.
In current machine learning research, the main approach that we take to, or the main area of research in machine learning applied to molecules is given some description of some molecular system. We mostly just build models that can, in one shot, predict multiple or single metastable states of this molecule. So in this case of this image here, we have a description of a alanine dipeptide. We would feed this to any model, and it would give us two different stable configurations that this molecule could be in. That's kind of like how you could consider this is that currently machine learning approaches kind of find the modes of the free energy distribution of these molecules. So in the case of alanine dipeptide, what a normal machine learning method would give us, it would give us these modes, which is in itself very interesting, but it can lack some information that could be crucial for further developing these systems. So one method that we then still heavily, or computational chemists still heavily rely on, is molecular dynamics. And molecular dynamics, instead of just giving us a single sample from the mode, can kind of give us more, like by integrating the Newtonian equations of motion, can give us a wider range of samples around these modes. But because of the computational expense of molecular dynamics, we're still often limited in how many samples we can get and how long we can let this process run. So machine learning has kind of like considered how to further develop molecular dynamics to increase its sampling range. And it's in the form of neural force fields, where we can sample a wider range of this free energy landscape, which is great, but it's still not enough when we consider some transition paths. Because if you consider these two alanine dipeptide molecules, I'm not sure if you can see my mouse, but I think it should be fine. So if you consider these two alanine dipeptide molecules, perfect, thank you, Anders. Then we can see that they are in two different wells. We can also see that there's some low energy area between them. So what we kind of would like to do is that when we sample with any method, that we also get samples along this trajectory, or that we maybe just get trajectories from this along this path. And that's kind of what we want to do with our work. So we want to sample these states along these transition paths. And down the line, this is for example, when we want to calculate how much energy we need to put into the system to transition between those two states, then we need to first of all find these transition paths between them. And then the second step that we want to take in our work is that we don't only want to sample the transition paths, but we want to do this without adding any prior information to the method. So in the example that we have on the screen right now, what I'm displaying here is a free energy landscape of these molecules based on two angles within the molecule. So if you consider these two samples, we can see that they differ from each other based on the rotation of this and this bond. So we can plot this free energy landscape of these two molecules based on these two angles, and that gives us some intuition about the method, about how this transition path would work. However, this does require some prior knowledge about how this transformation happens, and this we kind of don't want to use this within the method that we're going to propose. So we want to get rid of these collective variables. And so it's kind of the motivation of the work. We see that machine learning is giving great computational advances to to problems in chemistry and computational chemistry, and we want to take it a step further by sampling these transition paths in molecular systems, and we want to specifically do this without collective variables. This can skip this slide. This is same as I just said, but then in words. So that's what we did with our work. So this is kind of the contributions of the work, as well as the outline of the paper. Specifically in the talk today, we're going to be talking about, I will be giving an introduction into the problem of sampling transition paths on a kind of like more formal basis than we originally had in the paper. I will briefly hint at a relation between the problem that we're discussing and recent work in the machine learning community on the Schrodinger bridge problem. But I will spend more time on formally showing how the problem that we're looking at is related to stochastic optimal control and how stochastic optimal control provides a solution for this problem. And then are going to use that gained insight into stochastic optimal control to propose a specific solution to this problem of sampling transition paths. And then lastly, I'm going to look at some results that demonstrate that our proposed method can actually sample these transition paths for a number of different molecular systems of different scales. Yeah, so I'm going to start with the problem setup. First of all, a short background on molecular dynamics. So for those not familiar with molecular dynamics, what molecular dynamics does or is basically a tool for computational chemists to understand how molecular systems transform over time. So given an initial system, a molecule, with positions of the atoms and velocities of the atoms, molecular dynamics describe how these systems transform over time. And it does it in the form of, well, it can do that in multiple forms. So the form that we're looking here specifically is in the form of the stochastic differential equation, where we're going to be updating these positions and velocities at every time step following these rules. So our positions are updated based on the velocities, and the velocities are going to be updated based on this a change in the potential energy of our system. A potential energy of a molecular system is built out of a lot of different components, can be van der Waals, potentials. Yeah, a lot of different aspects go into this potential energy that kind of like describe how we should be updating our molecule based on these forces. And the velocity is also updated based on this Langevin thermostat, where we have at every time step we take some velocity out of the system based on the friction that's determined by this gamma constant. And then we also add a form of stochasticity into the system, where this W is a Brownian motion. This is the variance, which is again dependent on gamma as well as the temperature T. And with this thermostat, we kind of like, well, Langevin thermostat is mostly used in molecular dynamics to keep the system at a specific temperature, which is the exact details are not important for understanding the work further. But what is important is to note that calculating this computational computing this potential energy U can be a very expensive operation. There are tools available that do this quite quickly, like for example, OpenMM is a common framework which integrates very nicely with Python, but it remains even with these optimized packages a very expensive tool. Yeah, so that's just a quick note about molecular dynamics. But what molecular dynamics gives us in our case, where we're interested in trajectories and not in single states, is that given an initial state, x0, which is then again velocities, positions and velocities, if we just integrate these forces, we generate trajectories, and these trajectories are distributed according to this specific distribution, where we have our initial Gibbs distribution. So that this is just yeah, the initial distribution of our starting states, and then a transition distribution at every time steps. And this transition distribution is determined by this stochastic differential equation that we just saw before. So this gives us a distribution over just trajectories starting at any point at any random a trajectory starting at any random initialized configuration. However, what we're interested in our case is we're interested in transition paths that go from a specific given initial state to a different target state, or a distribution of a target initial and target states. So we need to kind of like add some things to this distribution over trajectories to get the distribution over transition path distributions. Right, so now we have a set of initial states R. So these can be the reactants of a chemical reaction, can be native states of proteins. And we have a set of target states P, which would be the products of the chemical reactions or folded proteins. And we have this potential energy function U. Then our transition path distribution is that distribution that we saw before. That's defined over any initial and target, initial and final state. And then we add some indicators in front and on both sides, so that now we only have distributions that start and end, trajectories that start and end in states that we want to be starting and ending in. And we can very naively sample from this distribution by starting with a sample from our set of initial states R, then just following MD, and then just check at the end, are we getting initial state, final states that are in the set of our target states? And if so, we accept this trajectory, and if not, we reject it and we sample again. And doing so, we would get samples from this distribution. The only issue is that in most systems of interest, we run into the problem that there's some kind of high energy barrier between specific initial and target states. So if we go back all the way to this distribution of alanine dipeptide, we see that if we want to go from this point here to this point here, we now kind of need to cross this barrier in the middle of high energy. And this barrier of high energy is going to cause problems, because it means that if we just randomly sample trajectories starting from here, they will very rarely actually end in the target state. So just very naively sampling from this distribution, is not going to work. So we need a smarter system for sampling from this specific distribution. And this is, at this point, we can kind of consider two different disjoint methods for doing so. One method is what Hannes just kind of pointed at before the presentation, is you can use some smart MCMC-based method to sample from this distribution. There's a ton of work on this called transition path sampling, where you would, I'm just going to point towards transition path sampling. There's tons of work on just doing this based on MCMC methods, where I directly sample from this distribution. But then there's another strain of work, which you could call biased enhanced transition path sampling, which the method that we're going to be looking at is more closely aligned with. So in the method that we propose, we're going to be adding a learning component to this stochastic differential equation that we saw before, where we're now going to add a bias potential to our original potential U. And this bias potential is what we're going to be learning in the end. So now with this bias potential added here, samples sampled according to this SDE are no longer going to be from this original distribution, but they're going to be sampled from this distribution. And quickly, I need to specify this because it's otherwise you're never going to understand it. this bias potential B is going to be learned such that if we sample an initial point in our initial set of states of interest, then with this bias potential B here, these trajectories should always terminate in our target set. So that's how this bias potential B how we will learn it. Well, that's the target. That's what we want to learn with this bias potential B. And if we do this successfully, then this bias trajectory will be sampled according to this distribution here. But now we always start in the initial set R, and our transition distribution is also incorporating this bias potential B in its update step. So this gives us a very specific method of learning or finding a distribution of trajectories. And there's a bunch of work in computational chemistry that consider this problem of learning this potential B or biasing your trajectories in a certain way. So I've highlighted two different works in this area from the computational chemistry literature here that I think are very informative if one wants to look further into this line of research. One is called non-physical sampling distributions in Monte Carlo free energy estimation, umbrella sampling. So this is about a method called umbrella sampling, which if this is your free energy of or potential energy, whatever you're looking at, of your system, it kind of adds little umbrellas at every time point and biases the sampling in that way. And another work is called Escaping Free Energy Minima by Alessandro Laio and Miguel Parinello, which is called metadynamics. That's the method they propose here, which is quite informative in how it works. Then we can take 30 seconds to look at it. So consider this potential energy of, well, this toy potential energy basically. And imagine that we have a state on this side and a state on this side of this barrier. And if we would be running molecular dynamics, we would be kind of like just jumping around in this well over here and never really crossing the barrier to this side. Well, we do want to make this transition because that's the transition path that we want to sample. What molecular dynamics does, it just keeps adding a little bit bias potential term at every, while learning. It slowly fills this well. And while it does that, the probability of sampling this distribution goes up. So that's kind of like how you can imagine these bias potential, these bias potential systems to work, where you have a initial distribution or initial potential energy, and these bias potentials kind of like fill in these gaps in the potential energy such that the distribution along the paths becomes uniform. So yeah, these are two very informative works if you want to have a closer look at these bias enhanced transition paths methods. So, but where does it leave us? So until this point, I kind of have done not much besides defining distributions. So we have the transition path distribution, which is this is not the transition path distribution. This is the transition path distribution, where we have this distribution which starts in one state and ends in another state. So imagine this being here. And then we have a bias potential enhanced transition path distribution, which needs to learn a bias potential B, such that every sample starting, every trajectory starting in our set of states R ends in our target states. So we need to learn this bias potential B somehow. And since we're looking at two distributions, a very expected thing to do is we're going to be minimizing a KL divergence between this distributions of the transition paths and our bias potential enhanced transition path. So that's exactly what we're going to be doing in this work. We have this distribution over transition paths by star, and we're going to be learning a bias potential B, so to minimize the KL divergence between those two distributions. And this is also where we can kind of directly see a very close relationship to all the work on the Schrodinger bridge problem that we currently see in machine learning research. So we have two distributions over trajectories, and we want to find a KL divergence between them. And if we consider that this pi star here needs to start and end in specific states, so they have predefined marginal distributions, then seeing that the problem that we're solving here is directly the same as the Schrodinger bridge problem, is quite trivial. In the updated paper, we will spend a little bit more time on setting up this relationship, but I just wanted to point it out here just to get your interest up. What we're going to be doing instead in this work is not looking at the Schrodinger bridge problem, but we're going to be using stochastic optimal control to find this policy B that minimizes this KL divergence. And one more thing is that we're going to be doing this without using collective variables. So I hinted at this before, is that in most cases, we kind of have an intuition as to along which bonds or which atoms, like in which points in the molecule we need to make these transformations. But we're not going to use this intuition that we have, because once we go to larger systems, this is not going to be work. Hannes, question?
Yeah, so Lars, I thought one of them, or the main purpose of doing transition path sampling is to find collective variables. So why are you saying that we do transition path sampling with collective variables?
So said before, there's like these two strands of research in well, there's a few more, but there's two main strands of research here. There's the strand of research called transition path sampling, where we directly sample from this distribution by using MCMC based methods. And there you often don't need collective variables, but you need something called order parameters, which define these initial and target states.
Yeah.
So these methods most of the times don't use collective variables, but once you what these methods give you in the end are distributions over are just samples of these distributions.
Yeah.
What's often more interesting is getting actual quantities along these distributions. So we, for example, looking at this method here, you might want to know how deep this well is.
Yeah, but I mean, so what I imagine is I do my transition path sampling, I have all my transition paths, and then I use the transition path ensemble to find some collective variable, and then I use that collective variable, for example, in umbrella sampling to get a free energy difference between these two wells.
Yeah, exactly. So that's kind of a two-stage step. You use transition path sampling to get the collective variables, and then you use collective variables to do the umbrella sampling or any other form of this bias potential enhanced sampling. And these methods So you needed that to the double step. What we're trying to do with this work is to not require both steps. So we're going to be learning both the bias potential,
Okay.
as well as the, like, without. So we can kind of consider our work to be part of this bias enhanced transition path sampling, bias enhanced transition path sampling, without needing to do the transition path sampling step beforehand. That gives you the collective variables.
Okay. Yeah.
Yeah. So it kind of combines these two steps of learning the collective variable and then using these collective variables to extract interesting properties.
So you're basically
kind of
just learning, you're trying to learn the optimal bias.
Yeah.
For that's your reaction coordinate. Yeah.
Yeah. And this this optimal bias is applied in theory across over the entire geometry of the molecule.
Okay, and then how I would use it is I would sample many paths with your bias term, with your learned bias, and then I would integrate along these paths the like I would calculate the probability of going this path and then somehow end up with a free energy difference between the wells.
Yeah. So that's what we're currently working on, is like extending this. Now that we have learned the transition paths and we learned this bias potential, how do we go from those policies directly to quantities of interest?
And what sort of systems can you use there or try this on? Like, well, between which wells? What are the wells then?
The wells could be any molecular system of interest or any system of interest. This is still like active work where we have this method for sampling these transition paths and learning this bias potential, and now we want to use those methods to actually derive these quantities of interest.
Yeah. And you don't want to say like what test systems you're using right now?
No, at the moment we're looking at like these very simple systems of like double well potentials, Leonard-Jones potentials, like very simple physical systems for which we can both qualitatively and quantitatively actually validate that the method is giving the correct potential, like quantities in the end. Yeah.
All righty, thanks.
Yeah, so this is kind of where we left off, is that we want to learn these collective variables, or we want to learn this bias potential without using collective variables. So that brings us to the actual method that we will be applying to learn this bias potential, and this is going to be based on stochastic optimal control. So a very short primer into stochastic optimal control. In stochastic optimal control, we're interested in some arbitrarily controlled system. So here we have some system X that is governed by the stochastic differential equation, where we have some dynamics of the system F. We have a control U, and we have Brownian motion that has some stochasticity. And then we're interested in finding control U that minimizes some expected cost over trajectories defined by this system. And this controls this expected cost C. In our case, we're looking at a specific branch called path integral control, where this cost C is defined as follows. We have a terminal cost phi and a quadratic cost on the control itself. And then, just to clarify, this epsilon is kind of like the amount of noise added at every time step by this Brownian motion. So this is a very specific branch of stochastic optimal control. And why we're looking at this specific branch of optimal control is because it gives us a direct connection between solutions to this problem. So finding this minimal control, or this control U that minimizes this expected cost, and the transition path problem that we looked at before. Specifically, is that if we use a terminal cost that is, let me back up for 1 second. So if we look at this controlled system here, X, you can see the close relationship to the molecular dynamics SDE that I've described before, where X would be positions and velocities, F would be the gradient of potential energy, U is our control bias control, bias potential B. This Brownian motion in our case had this Langevin term in front, but you can see the similarities between this SDE and the SDE that we had before. So if we exploit those similarities and use a terminal cost phi, so that's this terminal cost phi here, and use this logarithm of the indicator function, and use a very specific term for R, which is just so that it all works out, we find that the control, which we've now, the control U, which is defined as this bias potential B, then this control U that minimizes, that's included in this B, that minimizes this expected cost over this specific cost C, is the same B that minimizes the KL divergence between our distributions of our transition path distribution and our bias transition path distribution. So what this theorem shows is that if we use a method that solves the stochastic optimal control problem, so the problem of finding this U that minimizes the expected cost over trajectories, then that U is also the bias potential that minimizes this KL divergence, if of course we define everything properly. And in very short, this relationship can be quite easily shown based on this Girsanov equality, where we have that the logarithm of the ratio between these two distributions is basically this, and if we consider the control cost C, we've seen the similarity between, well, this part and this. So if we plug that in, we have a control cost C, which is this terminal cost phi and a logarithm of a ratio between two distributions. So it's quite, well, we just plug in some indicator functions, and then we kind of quickly get out this KL divergence. There's just one issue with this formulation, and that's this terminal cost phi here, which is a logarithm of an indicator function. So this is really only defined when transitions actually reach a target state, because only then is the indicator function 0. Well, yeah. Nevertheless, if we use some nice smoothing method or like some smoothed approximation to this terminal cost, it should all still work out relatively well. So in the work, we propose a method called PIPS, which uses this insight of stochastic optimal control theories, providing a solution to the transition path problem based on work from Kappen and Ruiz. We derive an explicit expression for this optimal control, which is based on re-rating samples induced by an arbitrary control U. And I don't want to go into too much detail here because it's kind of like takes away from the main topic of the work. But what's important to notice here or know here is that we can directly minimize this with using this method from Kaplan and Ruiz. We can directly minimize the KL divergence between the optimal control distribution and this parameterized distribution, which is parameterized by a bias potential B. So this gives us a method for solving the stochastic optimal control problem, and then by extension also our bias potential enhanced transition path problem. Some implementation details about this, just because it's important to see. As I mentioned before, this terminal cost that we use is quite ill-defined, and so we need to smooth it somehow. And for this purpose, we use a exponentiated pairwise distance, so that we now have some notion of a terminal loss, also when we don't reach a target state. And then the second important bit is that in our definition of this bias potential enhanced distribution, you saw that we don't directly depend on this bias potential, but we depend on, let's see if I can quickly skip back to it. We don't depend directly on this bias potential here, but we depend on the gradient of the bias potential. So this kind of gives us two options for how we're going to parameterize this bias potential. One is that we're just going to be directly, so this gradient of the bias potential, which we denote here by also B, but a bold B, is known as the bias force. And we have two approaches for parameterizing it. So we have, we can directly parameterize the force itself. So this would be a network where the output would have the same dimensions as the number of atoms in the system. Or we could be parameterizing the bias potential. So now we would just get a potential energy for every system, and then we get the actual bias force by backpropagating through the network. So this is two different approaches you could take to parameterizing this bias force. And we tried both of these methods, and we will see that now in the results. So in our work, we look at three different systems: Alanine Dipeptide, Polyproline, and Chignolin. And these three methods all have all range in their size. So Alanine Dipeptide is quite small, Polyproline is slightly larger, and Chignolin is slightly larger than Polyproline. But what it also means is that for Alanine Dipeptide, for example, we know the collective variables, and we can evaluate it based on these collective variables. For Polyproline, we also know the collective variables, but they are one of many possible collective variables. And then for Chignolin, we actually don't really have any idea of what the collective variables are. So this is how those three differ. So first of all, we looked at Alanine Dipeptide. Just a quick recap. So this is the molecule that we also at the beginning. So it has two different possible states, or two possible states that we're interested in. I see there's a question.
I want to note that there are Markov state models for Chignolin and larger proteins where we know the Boltzmann distributed transition paths.
Okay. Do you know the entire transition paths and all the collective variables?
Yes.
Then
the Markov state model for everything, folding, unfolding. You even cited the reference as the gold standard for different proteins folding. Yeah.
Okay. Maybe I've misunderstood something, or I've not clearly explained it. Would happy to talk about it after, because that sounds very interesting. Is it all right if I continue with my talk and then come back to that? Because it seems like it's quite a big big thing.
Sure.
Yeah. Okay.
Okay. Well, could I interrupt there? Like, Eugen, can you maybe explain a little bit? I cannot now immediately follow what you're referring
Okay.
to.
So
Like,
I work on a more traditional approach to this transition path sampling without a priori information. And there are a lot of papers. What I mean is Markov state models based on very long molecular dynamics simulations. So there are like the D-Shore group and with Markov state models on top of it, which creates then like a mean first passage times and paths related to that. So you can you sample very extensively the whole protein, including Chignolin and larger proteins. You will have a Markov state model, and that Markov state model you define folded, unfolded, and you will get a bunch of transition paths as a Markov state model. And
yeah. Like, so I have to imagine these MSMs that, for example, also Noé has in all of his papers, where we then have our transition probabilities between the states of interest. And then, yeah, you can look at those. And how is it now like related to the transition path sampling here?
Oh, so you can analyze these transition probabilities. You can convert them to transition probabilities from A to B, and for each probability, you would have a separate transition path. Then you can find the most probable, the actual Boltzmann distributed probability of a transition path. And find
but that's just because we ran our MD simulation for so long that we've just observed all the paths.
Yes, but I consider that as a ground truth. And if you find some other transition path, then it's not accurate, at least not at that temperature.
Yeah. That's fair, but I think Hannes summarizes that correctly as being sampling very extensively from the Boltzmann distribution, and then
fair. Yeah. Of course, you can have a trade-off between speed and accuracy, but you should know your accuracy, and so.
All right, but I got the picture. Thanks.
Yeah, thank you. Still would be very interested in talking after, by the way. So yeah, for Alanine Dipeptide, we have these collective variables around these bonds here, where define the two different possible states that they can be in. There's one here and one here. So we want, or ideally, our method would rotate the molecule around these bonds without us pre-specifying it. And that's also what we see our method do. We see that it very slowly transitions the molecule along those bonds, transitions the barrier, and then kind of like falls back into the state. And throughout this transition, we see that the molecule itself kind of climbs up to a point of highest energy, which is somewhere around here, and then goes back again. Right, so we see that the transition mostly happens along these two predefined collective variables without much noise at other points. This kind of quick graphical interface. So this is a quick quantitative comparison to some molecular dynamic runs. So we have our method. Oh, sorry, Samar, question?
Hey, just a quick question. So the dynamics that you showed over there, was that after running many other simulations to train a neural network and then run, or was it just like one single run that you were able to do?
No, this is, thank you for asking that, because it's important to clarify. So this is a single, so we trained a bias potential on this molecule. So we trained it using our stochastic optimal control-based approach. And then this was one sample of a trajectory sampled with this bias potential incorporated.
So I was wondering how much more expensive is it to train to generate the data to learn the network as compared to running like one sample trajectory?
So if you would just sample one trajectory, it would fairly rarely actually make this transition. So because of this barrier in between the two states, you basically won't see this transition. So it is quite an expensive method to train. I'm not going to lie about that. But we can't just run MD to prevent this this training time. We need some method to transition here.
Thanks, that makes sense.
Yeah. So yeah, these are the two, the force prediction and the energy prediction methods that I mentioned before for how we can parameterize this bias potential. And we have three different methods of kind of like evaluating our transition paths. We have an expected pairwise distance, which is just evaluating if we actually made the transition across the energy barrier. So it's the pairwise distance to the target state. We have a target hit percentage, which is based in terms of collective variables. So here we evaluate our method using the collective variables, which we normally wouldn't know, but we can use them for evaluation. And then there's an energy transition point, which is the highest point of the potential energy along the barrier. So we want this to be as low as possible. If we just look at force prediction and energy prediction, as kind of expected, or maybe not expected, but we find that in our case, energy prediction works a lot better than straight up force prediction. I don't really know why this is the case. In the end, it's only a way of a difference in parameterizing the method. So it's some difference in the learning objective. But we found that energy prediction works better than force prediction. So we've been using energy prediction for all the experiments following this. And then we compare this to first of all, we compare it to running molecular dynamics with the same time scale as our method. So we used 500 femtoseconds for our transitions. And so we compare it to running MD for 500 femtoseconds. And we do this at different temperatures. And for MD, as expected, this is what I kind of like hinted at in the question from Samar. It's only when we really raise the temperature do we find do we actually start finding transition paths, or do we, what I mean by transition paths is, do we find that that MD can have simulation runs that actually end in the target state? Because before that, it rarely ever actually hits the target state. And while it does hit the target state, the trajectory has clearly just visited a lot of random positions, because its internal energy was quite a lot higher than we found with our own method. And then we also compared it to MD, but now we run it without fixed time scales. So now we just run it until it actually hits the target, so it actually transitions. And then we obviously find that these methods do hit the target because that's how they're defined. But they still require raising the temperature. And in that sense also that don't necessarily find transition paths that are representative for the energy that we're interested in. Lawrence?
Okay. I was wondering if there's some type of like explore-exploit trade-off going on where like you have to worry that your model is going to latch onto like a specific path versus like, explore all the possible paths. Or if that's not really like something that you end up worrying about.
It's something that I'm definitely worried about. It's a learning method, so these issues are going to be popping up. One example here is, for example, is there are two barriers here. Like I'm not sure if you can see it clearly on this image, but if you consider this barrier here, there's a high point here, there's a high point here, there's a high point somewhere in the middle here, but on both sides of this high point is a slightly lower barrier. I believe this is the lowest barrier, and this one is slightly higher. But if you consider the transition path ensemble, then there should be transition paths both on this side as well as on this side. Our method only visits one of the two. So no matter how we train it, it's just going to be visiting either this top path or this lower path.
Is there like a specific reason for that?
It's how I think it's a very clear overfitting problem, where, like just independent of the sides, the bias potential is going to be pushing it this way. Maybe with a larger network, this sounds completely opposite to what I just said. I think it's an underfitting problem, and we can solve that by using a larger network that actually can clearly distinct between finding let's say we have a molecule or a system at this point. If it would have had at that point get a random burst of from the Langevin thermostat heading in this direction, it should take this path. If it's given some random force in this direction, it might want to take this path. So it needs to be able to distinguish between just between specific states better, and that would hopefully give us a better transition path distribution. But at the moment, that's not the case. I'm just going to go look at our other methods because I'm seeing that I'm running out of time, but my laptop is also running out of battery, and I don't have a charger anywhere close, a socket anywhere close. So I have about 10% left. It's going to be exciting. So we looked at Alanine Dipeptide, compared it to molecular dynamics simulations, found that our method works quite nicely. Then we also looked at Polyproline, which has two possible states. We can have like a left-handed or a right-handed helix, and we're going to be transitioning from a left-handed helix here to a right-handed helix. This is a considerably larger system. And in the case of Polyproline, the main collective variables are the bonds that I've colored here. So there's two bonds. There's a red bond and a blue bond. It's really small on my screen, so I can't probably see it. And these are the omega collective variables that you will see along this line. So what we see is that now there's a lot more noise in the system, but we also see that the collective variable, the first collective variable changes here into the right state, and then the simulation goes on, and then the second transition happens. This is a lot noisier of a simulation, but we can still see that the right transition has been made. So that's, positive. And then also for Chignolin, which is a small protein, we can see that it successfully fully folds the molecule. We don't have any collective variables here to look at, but again, it's qualitative in terms of qualitative study. We find that it roughly makes the right transition. So with that, I kind of like to close it off. So yeah, what we propose in this work is PIPS. It's a path integral path sampling method where we use stochastic optimal control for sampling transition paths without using collective variables. And before I close off, I thought I would give two more pointers to what I would consider very interesting work in this area, which also goes beyond this the standard machine learning research on molecules. One was, I think, presented last week in the M2. Was presented last week in another reading group. I'm sure Hannes has linked to that. In the same one, was it here?
Yeah.
Well, that's even it's a bit embarrassing for me. Sorry. But time warp.
Perfect. We know the paper very well, and we also liked it.
Yeah. I couldn't attend last week. I'm definitely going to watch it back. But time warp from Leon Klein, who also looks at like sampling for longer transitions. And then also there's, which is coming from a machine learning perspective, but there's also a lot of work in computational chemistry where they are looking. So time warp is from the machine learning community looking at solving computational chemistry problem, the same thing that we're doing. But for example, in David Limmer's group at Berkeley, I believe, which is originally a chemistry group, they're also looking at using machine learning methods for solving problems. So it's kind of like coming from the other side, which I think is very interesting to see these two communities coming together. So yeah, but pointing at these methods, I kind of want to end it here. I see there's one more question.
Yeah, so is it possible to calculate the first passage time, the average mean first passage time to the rare event or the barrier crossing dynamics with your approach, like what in this approach?
So there's this is a very interesting question. So what we do in our method, and it's kind of like exemplified here, is we set a fixed tau. So we set a fixed transition length. So we learn to have this transition happen within 500 femtoseconds, for example, in the case of alanine dipeptide. So you can't. So finding this transition length is definitely something that we're still considering as how can we actually do this, because we need it. So yeah, we can't use our method to learn it because it's something that we specify specifically beforehand.
I have a suggestion, like have you first, I want to ask another question, like I don't think that you have considered a dynamic disorder in conformational fluctuations here in your model as such.
So can you say that again?
Dynamic disorder, like over fluctuating landscapes where the energy barrier between different like states as it rotates, bonds rotates and stuff, so that there can be energy barriers which can fluctuate over time.
Okay, no,
that is actually called dynamic disorder. And there are papers by Robert Zwanzig, and that has been utilized to study also this kind of problems, this barrier crossing dynamics. Probably you should
wait a second, please. So I also want to understand the problem that we're talking about now. So are you referring to, for example, if we have a transition barrier, or if we have some little energy barrier over, for example, if we have a carbon HHH rest and we rotate that by 120 degrees, and then we have some symmetry there. Is that a sort of problem you're referring to, or what?
So what I'm talking about some large molecules, and they
Yeah.
have many degrees of freedom.
Okay.
And if you want to study like Cosgrain dynamics of them, then one finds that that the rare event is of course the barrier crossing dynamics. But before the barrier crossing dynamics, it is possible for the this large molecule to have conformational fluctuations, and which gives rise to different states. And the energy barrier to this, like small energy barrier to these states, is kind of a fluctuating quantity.
Yeah.
Okay.
So you talk about an Arrhenius kinetic equation.
No, let's
and
not
the
get into
and the
but the
activation
one you
energy
just
is
said that.
time dependent.
Yeah. So
Yeah.
what we're looking at
So-
here is we're looking at specifically from one state to the other state.
Yeah.
So the bias potential is based on how to say this correctly. The bias potential is learned to transition from A to B in a certain time span. But it's, let's say that you do cross that first little barrier, right? There's still a bias potential applied at that point.
I see.
So in that sense, you also know what the bias potential is from going from like this intermediate point to point B. It's just that the transition length at that point has already shrunk a bit. Does that somewhat answer your question?
Yes or no. Let's talk about it sometime later.
Yeah, that would be great.
Well, my drawing is actually it's interesting. Okay. Oh, well then, we have one more. Let's go for one more question from Yeding, and then and reserve the rest of and from Summer. All right, Yeding.
Yeah. Thank you. Very nice talk. I have several questions actually. So the first is, it is trained by cross entropy, right? It's not trained by different of a target from with the target state, right?
The method is trained based on minimizing the k divergence between these distributions, and that's dependent on this this gradient update step here. And what you can see here is that it's so this is an expectation over distribution sampled from your based using your current policy. These gradients re-rated by this cost C, and this cost C is mostly determined by the target state, and this target state is mostly determined by the difference to your target state. So it is dependent on your target state.
So it requires that the distance with the target state must be differentiable, right?
No, it only needs to so it only needs to take the gradient with respect to your policy parameters, and your terminal cost is just used for the weighting of your gradients.
Okay, fine, thank you. I have another question, which is that your searching path, which is not a minimal path energy, right?
Yes.
Okay. So it's not it can not used for searching for a saddle point of a potential surface. So another question is, does this model is transferable, or it is trained for one protein only?
It's at the moment it's trained for only one molecule. So we trained one policy for alanine dipeptide, one policy for Chignon, extending it to be transferable between multiple systems is definitely something that's on the horizon.
Oh, thank you. But it can it be used in explicit solvent environment?
I don't see why not, because it just depends on how you so how this is implemented, and there is a link to a GitHub in the paper. Is that we we start with a random bias potential. We basically use this bias potential, give it to OpenMM as a kind of like an external force. Then OpenMM uses this to generate a bunch of trajectories. We grab those trajectories, calculate this gradient update based on it, update our bias potential, give this to OpenMM for the simulation, and then we keep doing this loop. So however you define your system in OpenMM, you could also use learn a bias potential for that setup.
Yes, it looks so. But does it?
Wait, can we maybe give Samar a chance to ask this question?
Okay.
Maybe you can also write your question in the chat quickly.
I do have to say quickly, I have 2% of battery left.
Okay.
Then
I would really prefer to maybe take this discussion offline, so we can use the last 2% of battery left of the last SVC. Samar, it would be great if you can either use the Slack, or I think Lars, or use the or reach him via email. Cool. Very nice presentation by Lars here. I learned a lot. I hope you did too, as we always do. And if you want to join the future reading group sessions yourself, all the information is down in the description. And yeah, maybe see you guys next week.